Our presenter today will be Sally. Anybody who has been lucky enough to have Sally Lloyd visit their lab will know that just like Martin, she's a bit of a wizard when it comes to microscopes and lasers. She's been working in ART since 1999, firstly for research instruments and then for Cooper Surgical. She spent much of that time presenting at congresses, visiting clinics around the world, and helping to run ICSI, biopsy, vitrification, and electronic witnessing workshops. She's not part of the commercial team at Cooper Surgical, but rather presents today on an applicational and technical basis. For the Q&A, we're also going to be joined by Olga Rezina, who is a biology MSc with a specialisation in embryology. She's worked as a clinical embryologist for over 20 years and helped set up several IVF labs in Russia and collaborated in research activities in human embryology. She's been a lab manager, but now first for Origio and then Cooper Surgical. She assists embryologists in the setup of their laboratory, performing audits and advising on the flow of different lab procedures. She's got a keen interest in sperm selection, vitrification of oocytes, embryos, blastocysts, as well as trophectoderm biopsy. And she's currently the embryology advisor for Russia, Nordic, and the Baltic areas for Cooper Surgical, Fertility and Genomics. Again, we're joined by Rachel, who joined us yesterday as well. She obtained her master's degree in clinical embryology and possesses over 19 years of knowledge in ART. This includes experience guiding, leading and managing IVF labs within the Asian region. Rachel joined Life Global and then Cooper Surgical as the Asia Clinical and Technical Support Manager. She's got a very keen interest in the IVF lab quality control, culture system and condition, and embryologist training. I'm now going to hand over to Sally for today's webinar.
Thank you for inviting me to present in this webinar. Today, we're going to look at how lasers are used in ART and how best to use them safely. We're going to look briefly at how lasers became to be used, what different applications there have been over the years, what important features you should consider when selecting a laser, and how we as manufacturer recommend that you use them as safely as possible in daily use, and what you can do if things go wrong. So to start off with, let's look at what type of laser we're talking about. In many medical fields, people use lasers for all kinds of treatment, from oncology and skin treatment through to eye and brain surgery. In the early years of ART, people played with various different types of lasers, some carbon dioxide lasers, some UV, some where you had to actually touch the end of the laser onto the specimen, but relatively quickly it was determined that a non-contact laser operating in the infrared not only ablated the specimens used in ART efficiently, but came with none of the other drawbacks seen with other lasers, for example, potential cross-contamination or potential DNA damage. So back in the days, lasers were first used to try and catch sperm for early micromanipulation techniques such as SUSI, and even to try to normalize an abnormal 3pN fertilization. We'll look at current techniques performed using a laser later on. So the clear benefit of having a laser and being able to apply these small, precise bursts of energy exactly where you wanted them was very appealing to many, especially over commonly used alternatives at the time, such as mechanical drilling using a sharpened pipette like a knife, or acidified tyrode solution. As a single laser in an IVF lab is often used for multiple techniques, it's important to be able to adjust the effect the laser has on the specimen. And you've essentially got 3 parameters that you could change to get different effects: wavelength, power, and pulse length. Now, wavelengths we've discussed before was decided a long time ago. All commercially available systems certified for ART use 1480 nanometers. The power of the laser itself will, of course, affect the amount of energy delivered to the specimen. And what we found with the Saturn laser was as we increased the source power from approximately 140 milliwatts for the first generation laser, up to 400 milliwatts for the current generation, the less overall energy deduced by the amount of power of the laser and the amount of time that laser was applied for, the less overall energy was needed to make a hole in the zona pellucida of a specific size. Or in the case in this graph, we adapted the pulse length, the time the laser is applied for, until we got holes in the zona pellucida of various diameters. And it was clear that significantly less energy was used with a higher laser power than with a lower one. So next we'll look at the various techniques clinics across the globe have used or are using the laser for. So all these different techniques have used the laser over the years to a lesser or greater success. The papers are available as well as textbook chapters if you want to learn in detail how they were done. But for now, we'll just concentrate on these highlighted ones, which we believe have the most relevance in clinical use today. Laser-assisted hatching and laser biopsy techniques share a common purpose, that is, drilling through the zona pellucida. Although laser-assisted hatching has been a controversial technique in the past, we're finding more and more clinics are performing it nowadays, especially on their vitrified warmed specimens. For biopsy, no matter which stage of embryo development you perform the biopsy, it is likely you'll use a laser to make an opening in the zona. The laser can also, albeit sparingly, be used to facilitate trophectoderm biopsy by firing on cell junctions to weaken the cell adhesion or until the sample breaks off. Lasers are also used in blastocele collapsing as part of the vitrification process. While there is not yet any consensus, it is suggested that collapsing or artificial shrinkage of the blastocele prior to vitrification reduces the risk of ice crystal formation and increases post-warming survival. And this can easily be done by a single laser shot to a trophectoderm cell junction, ideally away from the inner cell mass. Lasers are also sometimes used in place of some of the more complicated tests for sperm viability. In a non-motile sample, a single laser shot close to the distal region of the tail induces a reaction similar to Hoss-positive spermatozoa and allows the sperm cell to then be selected, prepared, and injected. So now let's look at things to consider when selecting a laser for your lab. Firstly, think about what applications you will want to perform now and potentially in the future. Different techniques require greater or lesser use of the laser and greater or lesser magnification in order to get increased precision. Depending on whether you're in a private or public centre, of course, budget may have a large effect on the type of the laser you can buy, which may in turn make the procedures more difficult to perform. Make sure that wherever you are in the world, your local laser supplier has enough experience and skill to be able to support you ongoing, as these lasers are complicated medical devices, and if they're installed or used incorrectly, they could have a massive impact on the patient samples. So an example here is whether a fixed or an active dynamic laser would be suitable for your applications. So as we have seen for blastocele collapse and sperm viability, one single shot is all that's needed. But what about laser-assisted hatching, for example? Now, in this rather crude example, and I apologise for my poor drawings, I have a laser which is fixed in one position, where the red cross, the target, is. I then am quite likely to hold my recently warmed and still collapsed embryo with a holding pipette, so I can use the micromanipulator to change the position. It is often quite difficult to precisely position down to a few microns the holding pipette, so it may take a bit of time to get it exactly where you want it. And then you can fire the laser and ablate the zona where the target defined. Great. But now we need to make more holes to increase the size of the opening. So slowly but surely we move the holding pipette. Oops, a little too much. Oh, there we are. And fire again, and we get our second hole. And again, and so on, and so forth, until we have the size of the opening in the zona that we wanted. So it's not impossible to do, of course not, but it could be very time consuming if you have a tricky micromanipulator or stage control, or if you've got lots of embryos to do. So with an active or dynamic laser, the target position on the screen is decided by the user, i.e. you decide where you want the laser to fire, you point and you shoot. For a single shot, you click on the screen and the laser will move to that area and then you can fire a hole. For a wider zona opening, perhaps for hatching or embryo biopsy, again you can click where you want the laser to start, but you also tell it where to end, thus creating a path or a channel for it to ablate. It can either be a straight line, or in this case, you can curve it to follow the arc of the zona pellucida. For zona thinning, i.e. not penetrating the zona completely, you just need to position it slightly further out so you don't break through all three zona layers. So depending on the application again, you may find that some combinations of microscope and laser optics will be better or worse than others. Here we see the entire blastocyst, but it fills the whole screen, and that will make it harder to do the micromanipulation. Here we get a clear image of the field of view, including both our pipettes, but probably we can't see enough detail to precisely position the laser where we want it. And now we have enough detail with a good field of view to do the biopsy safely. So let's talk a little more about safety. How can we be sure that when we apply the laser with the view to destroying a part of the cell, we're not damaging the critical parts? As we saw before, the wavelength is fixed. The power of the laser is largely manufacturer determined and fixed, and it is the time that we apply the laser for, or the pulse length, which delivers more or less energy. It's generally advised to make smaller holes rather than big ones, as heat will radiate out, perhaps not actually ablating the material, but potentially heating it up to a level which could damage the proteins and the DNA. Because in general, nobody can say what pulse length, what distance, what number of holes is actually safe, it's logical to apply only the smallest amount of laser energy necessary to do the job at hand. Now, obviously, the techniques permitted in each country or region may vary, so wherever you are, be sure to check the local regulations as regards which applications and even which lasers have been approved for clinical use. In general, though, there are many papers out there on all the different techniques for you to research and decide for yourselves whether the laser is a safe and efficient method of performing the particular technique you're interested in. So now let's look at what we can do as regards day-to-day checks on our laser. There are several aspects of the clinical laser which we should check before each application. Firstly, and perhaps most importantly, where is the laser going to fire? Now, I'm still not quite brave enough myself to go for laser eye surgery to fix my short-sightedness. But if I am one day, I would really hope that the person performing it got it in the right place. And we should be doing the same in the embryology lab. So as a manufacturer then, we would recommend these steps. First, get an empty dish and focus on a scratch or something on the bottom inside surface. You may want to turn off or turn down the light to better see the laser guide or the pilot laser. So follow your manufacturer's guidelines. In the case of the Saturn laser, you need to click the center of the red pilot beam. And when it moves through to the next 6 positions, in the case of an active laser, you click exactly in the center. In this way, we teach the computer how to move the laser to get to the particular part of the screen we want it to fire at. Next, we need to decide what pulse length and therefore how much energy we will apply. And once we've chosen a pulse length, the computer shows us the expected size of the hole in the zona pellucida according to the pre-saved calibration done at the initial installation. And this is a process whereby we teach the computer to link the various size of pulses with the actual ablation sizes. So first, we choose a hole size, perhaps a medium hole size, and we fire the laser and then change the graphic overlay to exactly the right size of hole. Then we do the same for a small and big hole, and we can repeat this step several times, which then actually gives us a graph showing us the points that we've made which correlate between pulse length and actual hole size. Then the PC, the computer, then uses these points to cover any step in between. So for instance, if I chose a pulse length of 0.8 milliseconds, the computer would expect to see a hole size of approximately 11 microns in the zona, and that's how it calculates and shows us these graphic overlays. Next, the optical system in the microscope could have a big impact on how easy the technique is that you're going to be doing with the laser. So here we can see that we're looking for those junctions between the trophectoderm cells so we can shoot the laser at them. But in this case, the image is so fuzzy and poor, it's difficult to see. Now, one thing I've noticed over the years is a widespread lack of understanding of how the microscopes in the lab work. There seems to be no obvious part of embryology training which covers the main equipment to be used. Instead, it's often a case of learning on the job. So in case you're needing to adjust the microscope a little to get a better image, here are a few things you can try. Firstly, there's a nice trade-off between light and contrast. If you close the iris on the top of the microscope, or sometimes on the condenser, and increase the light coming in, you'll often get a sharper image, so you can see those junctions between cells better. Adjusting the condenser height also means that the sample dish sits in the correct plane for that condenser objective combination. Also be aware that dust and dirt and oil and even fingerprints could not only affect your image, but also the performance of your laser. For more info on microscopes, we have in our webinar series one webinar dedicated to microscopy in the ART lab, which may well give you more tips and tricks to get the most out of your IVF microscopes. Next, the height of the sample can also have an impact on the energy which can reach it. The laser objective lens is designed to focus the laser beam at a specific point, a fixed distance above the lens. It's known as the working distance, or WD. And this is where the embryo should be to get the most efficient transmission of laser energy, and it's basically at the bottom of the dish. If the embryo is raised a bit higher, then the laser beam is no longer focused, and although you'll still get some laser energy hitting the zona, there won't be enough to make the size of hole you're expecting. Instead, you'll end up with a much smaller hole, and then you'll get to thinking there's something wrong with the laser, when actually it's just the position of the embryo in the dish. Now, if you have an active or dynamic laser, it is a good idea to periodically check that you get the same results, in our case, we're talking about a hole, at all places where the laser can move to. So I just do a couple of clicks with a sample embryo around the screen, making sure we get the same results. If you have a 1.5x or other extra magnification lens in the microscope, be aware that using it may change the actual firing position of the laser. Here we see the target being checked against the center of the pilot laser on a 40x. But then after changing to the extra magnification from the microscope base, the actual position changes on the screen. And if you don't check if it's moved, you may end up positioning the embryo back at the original target site, which could then be disastrous for that embryo. And then lastly, it's always a good practice to minimize the differences between the operators as much as possible. All lasers have tools in the software, whether they're predefined shapes or lines, or presets in the software which can be prescribed as part of your SOPs, so that you know that all embryos are being exposed to more or less the same amount of laser energy. So now let's look briefly at some basic troubleshooting that all operators should be aware of. Specifically here, I'm talking about an RI Saturn active laser, but there may be some crossover with other lasers. So firstly, if you think your laser is misbehaving, ask yourself, is there any kind of hole or no? If yes, is it the problem that it's in the wrong position? If so, then you check your microscope is set up properly, even if your port selector is slightly out of its proper position. This could have a large effect on the lasering position under 400 times magnification. You should check that the camera is still in its correct orientation. Again, that can change the expected position on the screen. And then make a realignment of the laser. If there is a hole, but it's smaller or bigger than you were expecting, and it's 99.9% of the time going to be smaller, check you're working more or less on the bottom of the Petri dish. Maybe even turn the laser up a bit. There is a bit of variation between specimens, making them more or less susceptible to laser energy. For example, a thicker, denser zona, or one that has been previously vitrified, will likely produce a smaller hole than you'd expect with a nice fresh one. If in doubt, though, you should check that the hole size calibration, or rather the computer's expected hole size per pulse length, is still saved. If so, and it's still misbehaving, it might be time to contact your local engineer for a visit. Now, if the laser isn't making any hole at all, then you can check that you can hear a noise. If no noise can be heard, check all your connections and try again. And if still nothing, you need to contact your engineer urgently. But if it is making a noise, if it is beeping at you, that means that it is actually firing, but seemingly the laser energy is not getting through to the embryo. So if there is a noise, the first thing to check is that you're on the correct laser objective. I know this sounds stupid, but the number of times I myself have made the same mistake, I really can't count. Then lastly, check that the pilot laser is still in the same location that the computer-generated target thinks it is. And if it is, and you're still getting nothing, then it's time to call your local support team in. So just to summarise what we've covered today in a few points, there are quite a few applications for the laser which could help in your treatment of IVF patients. When you're choosing a laser, think about what your technical requirements might be before you decide which one would be suitable. Make sure you put in place procedures so all staff members are trained to operate safely and as uniformly as possible. So that's all I have to share with you today. There is a list available with all the papers we've referenced here. Please get in touch if you'd like a copy of this list. And thank you all for your attention.
Okay, thank you very much for that, Sally. It was really interesting. We've had some questions coming in throughout the presentation, but please continue to send questions in if you have any. So, Sally, I'm going to come to you first. You obviously talked about the different specifications of lasers, and you also talked about alignment and calibration. But we have had a question here asking, is there any way in which a laser can be calibrated to check the power? And are there any circumstances under which we would need to do that?
Hi, thanks, Colleen. There is a tool which we use at the manufacturing site to check the output of the laser before we ship it out, to make sure it meets our specifications. I've never heard of anyone using it in the field. Not even our own engineers have one and would take it with them. I would say it's more a case of an expectation of what your laser, of how your laser should be performing. So when I talked earlier about the hole size calibration, we're expecting to see a hole, for example, of this size. And then we come to our laser one day and the hole's really small. Something's changed. So you kind of go through that checklist of things I talked about. But if still you've still got that problem, then something has happened to the laser. And in some cases, often actually when a laser has been moved either from one microscope to the other, or it's moved location around the lab. Sometimes you shuffle the lab around to make it more efficient. Then dirt can get inside the laser, and if that happens and gets kind of, it can sap the laser energy coming from the laser box. In which case, then there's nothing really that the user can do about it, but an engineer could come in and clean it. Or it would have to come back to us really just to be cleaned down.
Okay, so basically, really, the only check that the user needs to be doing then is the alignment. Is that correct?
Yeah. Sorry. So that was to do with the laser energy. Right. The alignment should be done every single day that you use the laser. Turn on, or well, in our case, in the case of the Saturn laser, turn on that pilot laser, check it's in the right position. It takes about 10 seconds, that's all. And most of the time it should be in the right location. It takes a pretty big knock on the microscope to move it out. And if your microscope is moving often, then it's not tight enough and you need to get the guys to come back in and really tighten it up.
Yeah, so there's not really any other checks that you would recommend that the lab scientist would need to be doing on the laser?
No, the position, location's the most important thing. Align it again if it's not in the same position, and if it's not performing as expected, go through your troubleshooting checks, and if not, call the engineer.
Cool. I think that's an important point that you made as well, that it's important to check the alignment before the procedures, but you don't necessarily expect your laser to be significantly out of alignment. And if you find that it is consistently out of alignment, that's an issue to get an engineer in for, because it's possibly a sign that something somewhere is not quite tight enough, basically.
Yeah, exactly. And, we see it now and again, either in very busy labs where it's being used a lot, or being used a lot by people who are learning with the microscope. Also on really old microscopes, for example, all the inverted microscope have a knob normally on the bottom where you select the port that you're going to use, whether it's eyepieces or the side port for the camera, which is the one that you use when you're working with the laser. Now, that knob itself has kind of detent positions, click positions. So as you turn it, it clicks, and that's the position that it holds itself in. Now, that's great when the microscope's new, it's all tight, and it's got one perfect position. But over the years, those clicks and thousands of clicks can actually kind of widen that detent position. So, and when we're using the laser under 400 times magnification, the difference between that side of the detent and this side of the detent could actually be significant when we're working with a laser, and we could end up kind of having an incorrect firing position compared to the target. So with the older microscopes, you need to be a bit more careful.
Yeah, so I guess that's the same case really with microscopes then, that the more heavy the usage, the more chance there is for things to go out of alignment slightly. On that basis, how often do you normally recommend that labs have someone come out to sort of do sort of service and maintenance on the laser? And, would you differ those recommendations based on how much the lab actually uses the laser?
Yeah, I mean, sure, we've got, some of the labs that we work with are doing 50 cases per year, not all of which are going to be ICSIs. And then we've got, I know, labs where they do a double shift, working from 7 a.m. through till midnight, and it's just ICSI all day. So there is going to be a huge variety. For a normal lab, let's say 500 cycles per year, I would expect those inverted microscopes to be serviced annually, serviced and cleaned and maintained annually. But for heavy usage, I would be going for every 6 months.
Okay. The next question we have is a bit more embryology related. So I'm going to call on Rachel and Olga to give us some input. First of all, I'll just come to you, Rachel. Are there any concerns or any evidence that the laser has any impact on embryo development?
So far, there's no publications that shows that using laser on the embryos has caused any problems. And there are already thousands of children born, for those embryos that either have gone through assisted hatching using laser or embryo biopsy using laser. That's so far no publication to show that. That's sort of in a way to say that laser, it's pretty safe to use as long as the user use it correctly. I would say that. Yeah, that is very important.
Yeah, I think that's very important. That anytime we're using the laser, we're using it with the minimum energy and the minimum number of pulses that we can. Olga, I don't know if you've got any further input on that.
Oh, I'm totally agree with Rachel, and I think that laser nowadays, that's just a routine tool that we use in the lab every day. So we should use it in a proper way. That's it.
Okay, so we've got a couple of questions about Piezo. So I'm going to come to Olga about that. But first of all, I just want to get Sally to explain to everybody out there watching and listening what Piezo is.
So Piezo, I don't have a lot of experience with it because it's not been traditionally used in human. But I've worked with a few animal labs in the past where, for example, for mouse, it's really difficult to ICSI mouse in the traditional way. So they use a piezo drill. So the injection pipette comes in close to the zona, and then there's a small electrical kind of pulse, which then eases it through the zona and into the ulemma, instead of that quite a big push that we have to do with human, making the ulemma curve and then pulling back on it to break the ulemma. We don't do that with piezo. It saves that insult.
So piezo is basically an electrical current then?
Yeah, that passes down through the pipette and kind of causes the whatever it is to break.
Does the electrical current make contact with the embryo?
I guess so. I guess so. Again, sorry, it's not my. I haven't used one.
I've got somebody else saying no. I'm going to move on to just ask Olga a little bit about Piezo, because we have been asked by a couple of people if Piezo can be used for the same applications that the laser is used for.
Yeah, that's a really very good question. Thank you, Colleen. I'm not an expert in this topic as well, and I don't follow this topic because Piezo is not very popular device in Europe countries. Mm-hmm. But there are some publications from our colleagues in Japan, and as I can see, it's rather popular device there. And there are some publications, but there are old publications regarding this topic, and they used Piezo for hatching as well, for assisted hatching, by using ICSI pipette and vibration that goes to ICSI pipette. They used to make like a curve in zona pellucida, and of course, depending on the type of the pipette, the diameter of the pipette, they could create different curved areas, or different holes, the size of the holes in zona pellucida.
Yeah, so basically anything where we're looking to create a hole, they could be using piezo. And it's the electrical current is generating like a vibration.
That's vibration.
Rachel, is piezo used very much in the countries that you cover?
Piezo is actually very popular in Japan. I think most of the centers over there, they don't do the conventional conventional ICSI method when they do the injections. They will use the piezo. And of course, by using the piezo, the pipettes that they use for the sperm injections is kind of similar with the biopsy pipettes, which means it is actually not a sharp end pipettes like the ICSI pipettes, but it's a flat. Yes, it's actually with the electricity current, it causes a light vibrations. That is how they break so-called the ulema and deposit. Yeah, because for them, they believe in it and then they're doing it. And in Japan, most of the centers, as I mentioned, they're using piezo and they have great experience with very good results, in fact. Yeah, because they claim that it's less sort of like detrimental, to the oocytes. That's like force puncturing, just breaking gently of the ulema to deposit the sperm. Yeah.
Okay. Thanks, Rachel. That's super interesting. Sally, I don't know. Do you have any more on that, Sally, before we move on?
Well, only to say that, again, not very experienced with piezo, but that's because it's not. The applications that we use the laser for primarily are for bringing the zona pellucida up to temperature so that it kind of melts so that we can actually make a hole, whether it's for hatching or whether it's for making a decent hole in the zona so that we can then bring the pipette in. And I don't think that the piezo would ever be able to do that. The piezo can penetrate something. That's the purpose of it, but it's not for making a hole in the zona.
Okay. I've got a question that's just come in, Sally, which I'm going to bring to you, and I know you're going to be annoyed at me for asking it to you, but it's a question that we get asked a lot, and I think it's important to address. So this person is asking, what is the required and safe pulse in the laser to do hatching?
Okay, I'm not going to answer that question. I get asked, and I have been asked that so many times.
Yeah, it's important to tell us why you can't answer that question.
I can't answer that question. I mean, every laser is a bit different. Every laser setup is a little bit different. Again, there's variation in the zona, the thickness of the zona, the pulse length that each person chooses is going to give a different hole size. And then you've got a distance away from whatever critical cell that you need to be. So I would just say that overall it is better to use smaller holes rather than the larger holes. But then there's a nice trade-off between how many times do we insult the embryo, individual insults of the embryo, individual laser shots. Can't say that one. For laser-assisted hatching, I would just say the most people that I know who do it clinically on blastocysts after they've been warmed, just do it before the blastocyst re-expands so that you can see the ICS, well, you can see where the blastocyst is, and then just come to the opposite side of the zona so you know there's no laser energy going anywhere near any critical cells.
Olga, do you have any experience sort of using the laser for assisted hatching?
Yeah, I have my own experience, and of course, many clinics they use laser for assisted hatching for collapsing the blastocyst. Yeah, so basically, the main rule is that you shouldn't damage cells. To be honest with you, yeah. So if you can clearly see the borderline between two cells. So you should, of course, use this point to make a hole or to collapse a blastocyst. That's the main rule, and many clinics, they just follow this rule, and that's it.
Yeah. Rachel, is laser-assisted hatching popular in your region, and are there any rules that people follow?
It's actually quite common to do assisted hatchings over here. And usually what they do is they do not puncture the hole in the zona. What they do is they do a thinning. Yeah. And usually they will do it, say, on the day 3. So what they do is find a space in between with a large perivitellin space, between the 2 blastomeres, and then they just thin it using the laser. Yeah. So a lot of centers are doing that.
Okay. Another one for you, Sally. Someone asking just about when they're using their laser. Obviously, sort of focus is important, and you're looking down the microscope and they're looking at the screen. What can they do if the focus on the screen is not the same as down the microscope?
Okay, that often happens, and it's due to the location of the camera relative to the center line of the microscope. So if you look at where the camera joins to, there'll be like a C mount or a demagnifier there on the side of the microscope. There'll normally be some little screws that you can just loosen off. And then, so what I would do is I would look down the eyepieces and get the microscope focused really sharply on something, doesn't matter what it is, and then adjust the camera in and out until you've got the picture on the screen as sharply in focus as it is down the eyepieces, then fix it back in position. And of course, like anything to do with the camera with the laser, you need to then check your alignment on the screen afterwards. You may need to do another realignment. Only takes about 30 seconds or so. But if you move the camera at all, you'll need to do a realignment, or at least check it.
That's great. Again, a couple of questions really asking about the blastocele collapsing. I think it's pretty clear sort of how we do that. We're looking at one sort of pulse to the cell junction. But a couple of people asking about the evidence for doing that, and should they be collapsing? So just coming to you first, Rachel. In your experience, do most people collapse or not prior to vitrification?
I think this one is slightly depends on the protocol that one center is using, because I think now with all the vitrification protocols, some of them is recommending to collapse, and some is not. So I think for one center, whatever they're doing, first of all, just double checking, which one will give them the best results, and stick with that. Because again, there's no clear evidence that collapsing will give a better results. I think, we have seen that in one of our journal clubs. We also have a huge one whole journal club to talk about it, whether to collapse or not to collapse on during vitrifications. So I think the key point over here, yes, once we have been like one center, if let's say they are doing it, not collapsing, getting good results, I think they should stick with it. Yeah. If they want to change, must verify.
Yeah. And what's your experience of the collapsing versus not collapsing prior to vitrification?
To be honest with you, we have never collapsed blastocysts before vitrification, and we've got rather good results. And of course, I know a lot of clinics who do collapse blastocysts prior vitrification, and it's really depend on the preferences and depend on the experience, and depend on the results of the clinic. So, usually, if the clinic has experienced not very good results in vitrification program, so we usually recommend doing collapsing blastocysts before vitrification. So sometimes it gives really very good results.
Okay, great. Sally, a more technical question for you again. I know you probably can't answer this sort of directly. Somebody has asked, what are the current lasers on the market and the advantages and disadvantages of each? Now, I know you probably don't want to talk about, the different specific lasers, but if you could just sort of go over it again in terms of if you were buying a laser for your lab and you were doing, sort of biopsy, hatching, sperm viability, collapsing, what sort of specifications should the people that are selecting the laser be looking for? So what are the specific characteristics that they should be checking for that the laser that they're buying is fit for purpose for their lab?
Well, firstly, I would say that the current lasers used in clinical ART are very similar, at least. They're all using the same wavelength. There's a slight difference in the power that the lasers have, and therefore the amount of total energy that you apply. All the different lasers currently on the market they have both a fixed and a active or dynamic laser available. So that's kind of what that's how you need to think about what applications you're going to be doing, and also what your budget is, because of course there's a difference between the low spec and the high spec ones. But yeah, I would say if you're doing laser assisted hatching and you're doing biopsy, then I would be looking for a dynamic or active laser. And if you're just having it maybe for for the blastocyst collapse or something, then perhaps a fixed laser would be sufficient for your needs. Also, think about all the lasers. They come with software which enable you to obviously to see what you're doing, to make images, to take videos, to take measurements. There's lots of useful tools for in each of the lasers, and some lasers are kind of easier to use than others in terms of the interaction with the software on the screen. If you can, go and visit a lab close to you that's got one, so you can test all of the lasers, and then you can see which one would be most suitable for you.
Yeah, I think what you've said is very important. It's to try and get some hands-on time with the different laser systems before making a decision, because as you say, on paper the specifications seem to be relatively similar, and it's more in how intuitive or how difficult the software is to use around that has generally been my experience. Although, as you said, there can be a bit of a variation in power. And obviously, the higher power lasers, you would be using lower pulse lengths, whereas the lower power lasers, you would have to have a sort of higher pulse length to create a hole of the same size. Is there much of an impact of that? Does it equate to the same amount of energy expended, or? No,
it's not directly equated. In our experience, it's not direct. So a lower power laser uses a higher pulse length, but actually that kind of doesn't matter. It's the amount of total energy that you'd need. And in our experience with our laser, changing the different source powers of our laser, we actually needed more total energy to make the same hole size. Now, again, because nobody knows what is safe and what is not going to be safe, we've got to use the smallest amount of energy that we can to do whatever job it is that we're doing. So because of that, that's really why when we designed our laser from Saturn 1, 2, and 3 and 5, we kind of increased that source power so that we could use the minimal amount of energy that we needed.
Yeah. So you guys have found basically in that development process that the energy is the sort of power by the time, but actually the higher powered laser multiplied by the time is a lower overall energy than using a lower powered laser. Okay, good. I mean, I've always personally preferred the higher powered laser. And obviously, as you said, a directional or an active laser, that you can move around. And as I say, yeah, for me, the sort of intuitiveness and how easy the software is to use is a biggie as well, and how easily you can use that. More of an embryology question.
Just to add, just to share. Over here in this part of the world, a lot of the users, when they are considering to get a laser, one of the key questions they would ask is after-sales service. Because when they get a laser, they would be like, I'm not too sure how to use the software. I may not remember how how to do the alignment again, So a lot of the time they are asking for a strong support. I think this is one of the key as well, when they are anyone is considering getting a new laser. Just to add.
Yeah. And we just had a follow-up question as well, asking us to talk about the different softwares and which is easier to use and which isn't. And I think, again, that's just really a case of sitting down and using it. It's kind of like the difference between using an Apple Mac and using, Microsoft Windows. I might find Microsoft Windows easier and more intuitive. Somebody else might find Apple sort of easier and more intuitive. So I think in terms of the softwares, it's important to just sit down and have a play around and see which interface sort of works best for you. I'm going to go to Olga for a more embryology-based question. So it's back to looking at sort of assisted hatching again. And if we're doing assisted hatching, should we be doing it earlier in embryo development or at the blastocyst stage? This is just assisted hatching, to hopefully increase the chances of hatching and implantation. And also they're asking, if we do the hatching earlier in development, what can we do when we have where we have embryos that are hatching, where it looks like the ICM is sort of stuck, that sort of figure 8 with the ICM stuck in the zona breach? Is there anything you can do about that? And does that impact on the day you would hatch on?
Okay.
Yeah.
That's a huge question. But anyway, so let's start from the question about the day and will it influence or not. So first of all, if you look at the literature, there is no clear evidence in preferences in the day of hatching and so on. So basically, mostly, I think, people do hatching before transfer procedure. Yeah,
right.
If they do hatching just for transfer, so they do it before transfer procedure, and it really depends on them how they do it. Some of them, they do zona thinning, some of them just do whole, some of them just can use special enzymes, even sometimes to take off the whole zona. So many techniques and many preferences. Of course, if you do hatching for biopsy, that's another question, and we already talked about all of this here. So it depends again on the preferences from day 3 to even day 5. That's preferences in the lab. So about the questions, if we have ISM mass in this hole, so I would say I will leave this embryo like it is if we are going to transfer this embryo and don't do anything else. The embryo, the nature, will decide by itself what to do. Yeah, but that's my view on this.
Okay, that's great. I'll just finish up on this question basically and just come to Rachel on that. In terms of, you obviously said that assisted hatching is quite popular. What tends to be the practice? Is it, as Olga said, hatching right before transfer?
A lot of the time they would do it before the transfer. Yeah. So, but again, when they do it before the transfer, again, they have to be very careful. If we're talking about the blastocyst, because if, let's say, we're talking about expanded blastocyst, when we do sort of like hatching during that period of time, it's very likely we're going to hit the trifecta themselves, and then the whole thing would collapse. Yeah.
Yeah.
So a lot of the time, the strong preference over this part of the world, it's still doing it a thinning on the day 3 or even the day 4. Yeah. So
Okay.
it's, and hopefully with the thinning, we don't have the so-called problem whereby when during the hatching, it get the ICM stuck in between. Don't know what to do, kind of the situations. Yeah. So, yeah.
Okay, that's fantastic. So we have to finish up now, sadly. We've reached the end of our time for the session. So just to thank all of you guys on the panel, Sally, Olga, Rachel, thank you, all of you for giving the time. And also, obviously, thank you to everybody who has attended the webinar and for all the interesting topics